All right, so this is going to be a quick lesson on the mean value theorem for derivatives. Note that there's actually another mean value theorem. We actually quite often refer to it as the average value theorem for integrals. But don't confuse the two and try to see if you can understand what's going on here. So I'm going to give you a kind of graphical interpretation of this first, and then we'll see basically whether or not we can actually give a concise statement, or actually I'll just tell you what the concise statement is. So over here, let's draw this kind of XY axis. All right, now imagine that you have 2 points. So one point down here, one point up here. And you can flip them, you can make them equal. I'm just picking two different levels for convenience. So if I were to start over here at A, and I were to end over here at B, the idea is actually incredibly simple. If you draw some sort of continuous function, that means if you put your pen down at one point and it's a function, so it passes the vertical line test, right? And you just kind of go and never leave the page, right? And you draw a continuous function with the caveat that there are no sharp turns and essentially it's just differentiable. Then I'm going to make a very simple claim. There has to essentially be a tangent line that has the same slope as the secant line. In other words, if I were to connect these 2 points, right? So it doesn't matter what kind of function you draw. If I connect these 2 points, then I must have the ability to kind of shift this curve up or down and find at least one point in the interval from A to B that has a tangent line that is parallel to the secant line. Okay, so graphically what you're seeing is if I just kind of move it down, there has to be a point like that right there. That's going to be, one. Or alternatively, in this case, I have 2 points. Sorry, let me go back over here, click on that and shift it up. If I shift it straight up, then there could be a point over here. Then I would say I found at least this one point right here. So maybe that, I'll call it C sub 1. And this second point over here, I'll call it that C sub 2, where the tangent line has the same slope as that of the secant line. In other words, I'm saying that the derivative of the function, so if I call my function f, then the derivative evaluated at c sub 1 in this particular case will actually equal the slope of the secant line. And slope is actually just rise over run. So that would be f of b minus f of a all over b minus a. And this is from just algebra 1 topics, right? So this is your slope. And so the special caveat is that my c sub 1 will be between a and b. So you can try it for yourself. You can draw any sort of function as long as it is continuous and differentiable, right? So the precise statement is a little bit more interesting, right? It's very, very specific. But for those who want to know, if you have a function f of x is continuous on the closed interval from a to b and is differentiable, right? So differentiable on the open interval a to b. Then there exists some sort of c on the open interval from a to b such that, and the following statement, f prime of c, so the slope of the tangent line at that point must equal f of b minus f of a all over b minus a. All right, so this is the, again, very, very formal math definition of it. If you're confused about this kind of notation, let me just kind of show you what I'm saying here. This backwards looking E symbol just means there exists. It's shorthand notation. This little sideways trident looking thing is an element of. So element of. So it's just something on this interval, right? And so this is the full statement of the mean value theorem. It is the derivatives version. And this is quite, or used quite often. A lot of times, the most applicable version of it is when you pull the f of a equal to f of b. So if you were to say, hey, what happens if I were to look at a function that kind of goes like this? And so if we're looking at this value over here, and this is a, and this is b, and this is your function f of x, then it's very apparent that f of a equals f of b. So what we're saying is that if we're calculating our slope over here, f of b minus f of a would just be 0. So if you were to pull essentially a horizontal line between the two, then there should be at least one point, so at least one point on this interval from a to b, such that there's going to be a tangent line with a slope of 0. In other words, there has to be a critical point. And this is used for, again, Rolle's theorem, as well as basically finding local extrema and also absolute extrema. All right, so there we go. That is the mean value theorem, MVT derivatives version.